everyone, and welcome to the Joy of Abstraction Book Club, Chapter 19, Pullbacks and Pushouts. Gosh, what a long way we've got, and what a lot of fantastic questions we have. So let's launch straight in. I'm so happy that so many people are still really digging into this material. First question, do you know why it's called a limit? Second question, why are universal cones called limits? So there seem to be a couple of questions about this. Someone said cone makes more sense as it's more self-explanatory, but I'm having a hard time connecting limit to the content. And why is a universal cone called a limit? In what sense are they limiting? And so this is one of those things that's come from another part of math, I think. And if you haven't seen that part of math, then it may seem peculiar. And so it's important to think of limit not in the sense of the end. So it's not like this is the limit of my ability to lift weights. So it's not the boundary of the end. It's more like the limit of a sequence. So if you've done limits of sequences in calculus or analysis, then what happens is you have a sequence of numbers and they never quite reach somewhere. But I think that the intuition for convergent sequences and their limits in calculus is perhaps not always quite right. So the limit of a convergent sequence isn't the point that they're trying to reach in a way. It's not the kind of boundary of where they can't get to, because if a sequence is going backwards and forwards, then it's kind of the limiting point will be in the middle, right? So if you, for example, have a sequence that alternates positive and negative, and it might go 1 over n, positive and negative 1 over n. So it will go, and maybe I should draw a picture. Hold on a second. Let me share the whiteboard screen. So if you have a sequence that goes along the number line, say, look at that lovely number line. Here's 0. And so maybe it goes 1, and then it goes -1, right? And then it goes 1/2, and -1/2, and then it goes 1/4. No, it doesn't. It goes 1/3. Well, it can go 1/4 if it wants to. Let's make it go 1/4. 1/4 and -1/4, and then it goes 1/8 and -1/8, and then so it'll keep going like this. And so the limit of that sequence is 0, and it's not the limit in the sense of a boundary. It's a kind of limiting case. And so another way you can think of that is that if you've got a bunch of numbers with some relationship, the limiting case is some number such that they're all kind of heading towards it. And so that's why it ends up being kind of like a cone. So there are more technical intuitions behind this. If you Google the question, then some more technical things come up. But it's like, another way you can think of it is like the picture of when I drew the natural numbers and they go 0, 1, 2, 3, 4, and so on. And infinity isn't in there. But if we wanted infinity to be in there, it would sort of be up here. That's the limiting case of natural numbers. And you'd have arrows, all these arrows pointing to it. And so then that starts to look a bit more cone-like. And so that's what I would say about that. I forgot to say a couple of things at the beginning of this video, one of which is thank you very much to the Topos Institute people again. The other is that I'm sorry that I've got a bit slow at making these videos so that you really can't watch the previous video before submitting your questions for the next one. So I'm going to try and get a little bit further ahead next time. It's just that because these videos are getting longer and longer, I've been getting more tired from each video and then waiting till making the next one. So I'm going to try and catch up again this time, but no promises. And the other thing is I've got a new microphone. So I hope that this is better, and I hope it's not worse. Right, so that's questions 1 and 2. The third question, is division another example of a partial binary operation since you can't divide by 0? Yes. It depends what you're talking about, though. So you have to say what it's a partial binary operation on. So if you're thinking about, for example, on the real numbers, then division does not go from the real numbers to the real numbers, cross the real numbers to the real numbers. But you could just call it an operation on the real numbers with 0 removed. And I think that's a more natural thing to call it. Actually, I don't think it's that natural to think of division as a binary operation at all, because I'd prefer to think of division as multiplication by the multiplicative inverse, but that's a separate philosophical issue. Right, that's question 3. Question 4. At the beginning of 19.3, you reiterate all universal properties are terminal objects somewhere. By duality, aren't they also initial objects somewhere, namely in the opposite category? Is there a sense in which it's more natural to emphasize the category in which they're terminal rather than initial? So in 19.3, I am talking about limits, and that's why I said terminal, because it is more natural to think of limits as terminal objects, because then you don't have to turn things around. So technically, a terminal object is a limit. It's a colimit in the opposite category, but in that actual category, it is a limit. And so in 19.3, I'm introducing pullbacks, which are limits. And so I'm talking about the universal property as a terminal object. Yes, that means it's an initial object somewhere, but it's better to, I think it's better to think about these things in the category where you are drawing that direction of the arrows in the most natural direction. So a function from A to B, yes, can be regarded as a morphism from B to A in the opposite category, but it's odd to draw the arrow in that direction. So I would rather talk about those arrows as functions from A to B. That said, whenever you think about a concept in category theory, it's good to have in mind the dual at the same time. So if someone says something is a terminal object, you can simultaneously know it's an initial object somewhere else. And that's a good thing to be able to do. So that's question 4. Question 5, how should I be thinking about quotienting? I think about quotienting as when you've got some relationship between some objects and you want to kind of consider all the related objects to be the same. So it's like you're really forgetting that they're different and gluing them together, smushing them down, smashing them down so that the related things are really treated as the same. Not just treated as the same, but they really are the same. And that's why it's kind of violent. You're really smushing something down. So I think of it as smushing something down. So that's, yeah, and it's kind of, you lose a lot of information because you're really, really sticking things together. That's what I would say about that. That's the first 5 questions. Okay, there are 14 more questions. Let's see how many I can do before I need a break. Woo! As soon as I said the word break, I spontaneously needed a break. Okay, let's see. So the next question, page 272. I found it very helpful to use your example of matching pants and shirts to try and understand the objects and morphisms in the general case of the pullback. If I'm understanding correctly, in this example, so let's have a look at page 272. In this example, the object V would be the set of all matching pairs, and V seems to be the largest of the sets that match. Is this always the case, and is the factorization K always an injection or monic? Right, so in this diagram, V, what we've got is, this is the generic pullback diagram. And the fact that it's a pullback means that for any X equipped with morphisms going like this, making the outside commute, there's a unique factorization K. So I would say that it's not quite right to think of V. So the idea is that if A is pants, wait, which way around did I do it before? Yeah, pants. And B is shirts, and this is color, then you want all the pairs of pants and shirts that have the same color. And so V is the maximal set of such things among the ones you own. So if somebody owned more of them, then that would be different. So this is this is where the real life situation breaks down a bit, because you could have a set X where someone just had several several copies of the same pair of pants that you have, in which case they might all map to here, and they might also have several shirts that are all various copies of the ones you've got, in which case this wouldn't be injective anymore. Okay, so let me see if I can make this into a real thing. So perhaps you have red pants and you have blue pants. So these map to the colors red and blue. And then you also have a red shirt and a green shirt. So those map to red and green. So we've got colors red, blue, and green here. Oops, that looks like Gren. So then the pullback is the set containing just the matching pair, red shirt, red pants. Okay, that's the pullback. But then this set X here could be anything. So it doesn't even have to be a set of shirts and pants. It's just anything that comes equipped with morphisms like this. And so it could be that someone here has a red shirt 1 and red pants 1, and that they also have a red shirt 2 and red pants 2, and that this function sends everything to the red pants, and this one sends everything to the red shirt, so the outside commutes for them. But then this will not be injective, because red shirt, red pants will go to red shirt, red pants, and red shirt 2, red pants 2 will also go to red shirt, red pants 2. And so this set is the maximal set of matching shirt pant pairs that you have, but somebody else might have more of them, I guess is the point. Okay. Next question. Do the squares on page 273 commute if the fibered product is the empty set? Right. So, for example, someone said, if we only had blue and yellow shirts and you have orange and green pants. Suddenly freaked out that I'm not recording. Periodically, I have to freak out whether I'm recording or not. Okay, I am recording. It's all right. So then we've got blue, yellow, orange, green, and nothing meets up. So the pullback is indeed the empty set. So now the question seems to be, does this still commute? And so the answer is, I think, why does this still commute? Because it has to commute, because that's the definition of a pullback. And here's why it commutes. Do you remember about functions out of the empty set? Right, the empty set is the initial object in the category of sets. So there is only one function out of the empty set. And so this diagram commutes because they are both ways round produce the empty function. There is only one empty function. And remember, there is only one empty function because a function says for every element in the source, we have to assign an element in the target. And if you have 0 elements in the source, then you are vacuously done by the time you've said for every element in the source. And so that is your function. So the all 0 elements, right? Every element of here ends up in the same place, no matter which way around this square you go, because there are no elements. So it is vacuously satisfied. That is questions 2 and 3 of the next part. So Page 273, does the product being fibered refer to restricting ordered pairs A and B such that A and B are mapped to the same place in C? Yes. So the idea is that a fiber is like a pre-image. So the fiber is everything that sits over blue. So it's everything that's blue. So the fiber over blue here is everything in here that's blue. And the fiber over orange here is everything that's orange here. So when you take a fibered product, you're taking it fiber by fiber. And so the stuff that sits over blue in the end consists of the stuff that sits over blue in this direction together with the stuff that sits over blue in this direction. So if there is nothing sitting over blue in this direction, you don't get anything. So in this example here, the fiber this way over red is this shirt, and the fiber this way over red is these pants. And so in the fibered product, you take the red pants with the red shirt. You don't take the blue pants with the green shirt because they're in different fibers. And that's kind of what fibers means. Fiber bundles, I can never quite remember what they are, but they're a similar kind of thing where over each fiber, you take some bundle of things. So if it's a vector bundle, then over each fight, so you have a base space and then you have something sitting over it so that each fiber over it is some kind of vector space. Page 276 is the distinction between any old cone and a pullback extra commutativity conditions. So it's not quite extra commutativity conditions, it's the universal property, right? And so the difference between any old cone and a pullback is, here is the diagram that we're taking a cone over. This diagram is fixed. So this answers the second part of the question. You decide that you're going to take a cone over this diagram. So this diagram stays completely fixed. And then you explore other things having a relationship with it. And so then you go, okay, what about this cone? What about this cone? What about this cone? What about this cone? And then you look at, that's why morphisms between the cones only go here, because this blue part is the basic diagram that you're investigating. So you never change that. So the universal property isn't just a commuting condition. It's more complicated than that. It doesn't just say something commutes. It says for every something, there exists a something such that some things commute, right? And so it says that, I'm just going to make a huge mess of this diagram now. So the commuting condition says that for every cone, that's this big green one, there exists a factorization such that everything commutes. So I hope you can see that it's not just a commuting condition, it's an existence. It's a for all there exists such that something commutes. That's a lot more than just a commuting condition. Page 277. Before reading the footnote, I was thinking the elements in C1 were morphisms such that F would be a composite. So I'm trying to invoke my psychic powers here, and I don't think I'm doing very well. Page 277 is about using a pullback to define the composition in a category. And so what we're doing, let me get the blue back again, is we're taking morphisms of C1. So this is where we're defining a category by a set of morphisms and a set of objects and a source and target map. And so what we're saying is that we've got, what we're trying to model is morphisms F and G that meet up in the middle. And so what we're thinking is that we've got our two sets of, we take the set of morphisms twice. And so what we're thinking is that supposing we have an F that's an element of here and a G that's an element of there. So this question says, I was thinking the elements in C1 were, no, I don't understand the question, were functions such that F would be a composite. So it's not F that's a composite, we're trying to make a composite of F and G. So that's why we have to start with a pullback, because if we start with a pullback, we're saying we're taking a morphism and another morphism, and this is the source map, and this is the target map, such that the source of F is the same as the target of G. That means they land in the same place in C0. And so here I do get composable pairs. Someone else says, I'm inclined to label the arrows of the pullback F and G, but is this ill-advised since I meant to think of those arrows as projections? Yes, you are meant to think of those arrows as projections. And you can call them F and G as long as nothing else is called F and G. But if something else is called F and G, then that is ill-advised. And I like P and Q as projections because P is for projection and Q is the next one up. If you're doing ones with more projections, then you might go P1, P2, P3, P4, P5, for example. Okay. Question 8. Page 277, in the sentence in the middle of the page, our function for composition is defined on a pullback, which is a subset of the product, not the whole product. We're talking about Cartesian products here, not category theory ones. It's both in this case because we're in the category of sets. So in general, the Cartesian product of sets is one specific realization of the categorical product in sets. If you're not in the category of sets, then the pullback is always related to the product, because if you take this pullback, well, let's start with the product. So if you just take the product, then you're just ignoring B. So this is not a fibred product. It's just a product and it has no relationship with B. So unfortunately here, I have drawn a diagram that doesn't commute. If you then take the pullback, it happens to make the diagram with B commute, but the product doesn't care about that because the product's universal property just says, given any object and a pair of maps, there is a unique factorization, right? So there is always a unique factorization from the pullback to the product. And we could try proving that it's always monic. Now I'm going to have to pause for a second. Okay, good. I was not convinced by my ability to do that in real time, but I think I can do it now. So what we're going to do is we're going to prove that this factorization K is monic. So how do we prove that it is monic? Well, we have to consider two maps going into it. So if we've got F and G, so this has to be a fork. So we consider the point about being monic is we have to consider two maps going in such that F composed with K equals G composed with K. And we have to conclude, we want to deduce that F equals G. And so what we're going to do is name some things. S, T, P, Q, I, J. And so have a look at what we're trying to show. We're trying to show that if this equals this, then F equals G. And whenever you're trying to show that something equals something else using a universal property, the aim is to exhibit the thing that you're trying to show as equal as a factorization induced by the universal property. Because if this is a factorization induced by a universal property, then the uniqueness of the factorization is going to enable us to conclude that F equals G. So in this case, we're mapping into this pullback. So we ought to use the universal property of the pullback, in which case what we need is a map from X to A and a map from X to C such that the outside commutes. In which case we can invoke the universal property of this pullback to show that if F and G are both factorizations, then they must be equal. And so what can we do here? Well, there aren't that many options. So what we can do here is call this map, this composite, IF. And we can call this map JG, but let's just look at this for a second, because I is the same as PK. So this equals PKF, and KF equals GF. So this equals PGF. And similarly, JG, or J equals QK. So that's QKG, which is the same as QKF. And now let's see whether the outside of the square commutes. So if you go all the way down to S, then what you're doing is now I'm going to try and do this dynamically for you. So we're going down here and then S, but that's the same as doing F followed by I followed by S, which is the same as F followed by K followed by P followed by S, which is the same as G followed by K followed by P followed by S. I'm doing this wrong. Right, this square doesn't commute. This square doesn't commute. The outside square commutes. Have I used that the inside square commutes anywhere? No, I haven't. Good. Let me just do that again. So I'm going to go outside and then S, which is the same as F, I, and then S. I followed by S is the same as G followed by T. So now I can go F followed by I followed by S is the same as F followed by G followed by T, J followed by T, which is the same as this outside part. Let me just check that I didn't use this non-commuting square in here somewhere. IF equals PKF, which is the same as G. Yes, I think that's fine. So what we've shown is that the outside of this diagram commutes, and therefore there's a unique factorization from X to the pullback. So now the next step is to show that F and G are both factorizations. And remember that factorization means that both of the triangles have to commute. But let's have a look at this. Well, Fi equals this by definition. And what about F followed by J? Well, F followed by J is the same as F followed by K followed by Q, which is the same as G followed by K followed by Q, which is the same as G followed by J, which is the same as this outside part. And we can do the same for G. And so that shows that F and G both are factorizations for this thing. And because of the uniqueness of factorizations, they have to be equal. Now, that was quite fast, but it is a video, so you can watch it again. You can also slow it down. And I do encourage you to see if you can write it down for yourself, because if you didn't understand it, having more, it's one of those things where having more explanation doesn't necessarily help, but working through it yourself does, because there are so many things to see in this diagram. I could write out a lot of symbols, and I don't know that that would really help either. That's what I say about reading a diagram dynamically. So what we've shown is that K is monic. And monic, remember, is like being injective for sets. And so in the category of sets, the pullback is always a subset of the product, or isomorphic to a subset of the product. And then in a general category, there's a monic from here to here. Okay, well, I found that interesting. Question 9, page 278. At the beginning of the chapter, you give great intuition for pullbacks with pants, shirts, and colors. Talk about the example of when we want ordered pairs to meet in the middle. What is a similar intuition for pushouts? If we use pullbacks to make pairs coherent in some way, then why would we say, here's a situation where pushouts are helpful? It's really about gluing, I would say. So I give the example at the end about gluing in topology. And so a pullback is like a product where you refine it a bit. And so a pushout is like a disjoint union where you refine it a bit. And so if you have A going to B going to C, you could just take the disjoint union, but maybe you want to refine it a bit, and you want to refine it a bit according to which things all came from A. So in the pullback, you're trying to refine it according to oh, I didn't do very well with that notation, did I? Let me do that again and make the notation coherent with the pushout case. So what we're doing is we're saying that we're taking a disjoint union of A and C, but we want to quotient it out. Which page am I doing? 278. we want to quotient it out by some relation involving B. So in the pullback, we said, we don't want to just take any old product of A and C. We want to refine it according to where everything lands in B. So here we're doing the dual. So we're refining it according to where everything came from in B. I've just realized that because I'm sitting at my kitchen counter, I quite often end up sitting with a really, really strange posture. So I'll try and fix that. So we're trying to refine this disjoint union according to where everything came from in B. And so the example that I give about topology is where you can say, okay, I'm going to take, and what was the example that I gave? Okay, I had to restart my whiteboard, so I took the opportunity to get some chocolate. What was I saying? I was saying that here's a way we can use a push out in topology or in sort of life, that if we want to glue 2 strips of paper to make a longer strip of paper, if we want to give someone instructions how to do it, then we might say, put some glue here and stick it here. So it's like when you, it's a bit like when you do your own luggage tagging if you're getting on a plane, except that's only 1 strip of paper. So then instead of just making a disjoint union where there'd be no overlap between these 2 strips, you have, I don't like the placement of that. You have this notional blob of glue and you're saying, okay, that's going to go here and it's also going to go here, so that when you take the push out and you stick them together, those 2, it makes a long strip of paper that's not supposed to be that wobbly, and that join is in the middle and it's overlapping. So I think of pushouts as gluing, and it's much more complicated when you have algebra involved, because if, for example, this is actually a group and this is a group, then first of all, the disjoint union isn't really a disjoint union anymore, it's a co-product. And if you have a group here and a group here and you take the co-product, you can't just take the disjoint union, because you have to make the binary operation work on the elements of here together with the elements of there that you haven't got yet. And then if you are also quotienting out by an action of B going into A and into C, then the quotienting becomes way more complicated, because you have to quotient it and respect the group action at the same time. But the basic idea is gluing things together in the context of the category you're in, which is typically a lot more difficult than this example with strips of paper that I just gave. Okay, 5 more questions. 3 of the questions are the same question. So that means there's only 3 more questions. So there's things to think about. 19.8. Several people asked me to basically do it. So here we go. I'm going to go back to blue. I am going to take a sip of water because this is a little involved. And 19.8, things to think about. 19.8, which I did not work through in the book because it's not critically part of it. Wait, what page is this on? 278. See if you can express the axioms for associativity and identities in commutative diagrams. So what we're talking about is the alternate definition of a category where we have a set of morphisms and a set of objects with a source and target. And then we said that composition is a morphism from the pullback of C1 and C1 back to C1, making a certain diagram commute. So what it actually is that you have your ordinary diagram of a single set of morphisms together with the source and target. You also have the C0, C0. Then you have the pullback, and it's got a projection map to the first component. So that's like the first morphism in the composable pair. And this is like the second morphism in the composable pair. And then when you do the composition, the source of the composite has to be the source of the first map in the composition. And the target of the composite has to be the target of the second map. But fundamentally, composition is this factorization here. And so then when we're talking about associativity, what we're saying is we've got three composable maps, right? So this is a composable, this is a morphism, and another morphism that are composable. And what we want is three composable morphisms. And what we want to do is we want to consider doing the composite of the F and G first and then H, and comparing that with doing the composite of G and H first and then F. But the first thing to do is express a composable triple of morphisms. Now, how are we going to do that? Well, this is how we did a composable pair. So to do a composable 3 in a row, what we're going to do is stick on another pullback. And this kind of makes use of the fact that you can do a 3-ary pullback, because what we're really doing here is we're taking 3 copies of C1 and we're making them all each meet up in the middle in a different way. So this is the target of the first map equals the source of the second one. The target of the second one equals the source of the first one. And we take a giant pullback like this. So I haven't really talked about ternary pullbacks, but it's the same concept as a binary one. You can write it out as a binary one, whoops, followed, that's terrible. You can write it out as a binary one followed by a binary one, or not. You can just take 3 of them in a row. And then the universal property will be that if you have something up there with morphisms like this, then there's a unique factorization. So then what you do is you can either do composition on the first 2 and leave the second one the same, which takes up collapses the first 2 components and then leaves the pullback with the second one. I'm leaving out a little bit of detail here because it would take a lot more time to go through every detail. So there are some questions about what this means. So this morphism says do the composition on this component and leave the last one the same. But then in this direction, we want to do 1 crossed with composition. So in this one, we're leaving the first morphism the same and doing the composition on the second 2 components. But this also takes us to C1 pullback with C1, because the first component is staying the same and the second 2 are collapsing down to C1. So then you can just do composition. And here you can also just do composition. So that is associativity. And then for the identities, what we're saying is that for every object, we get a morphism such that some things have to commute. And so did I do it in the book? Oh, maybe I didn't. Maybe that's what someone's saying. For the identities, is it just the same diagram as for composition, just keeping F and the right and left identities in mind? So the identity says that for any object, we are going to have a morphism, but the source of that morphism has to be the same as the object we started with, and the target of that morphism, oh no, it's frozen again. This is annoying. Okay, I'm back. I hope that this doesn't crash again, because it's going to get really tedious if I can't finish to the end of these questions in one go. So what I was just saying is that to make the identities, we need a function from the objects to the morphism such that the source of the morphism we land on is the same as the object we started with, and the target is also the same as the object we started with. So that's how we express identities. And then we want to say that if we take an identity and compose it on the left with any morphism, we get back the thing we started. So what are we saying here? We're saying that if we, okay, so what are we saying for the identities? Secretly, what's going on is that we're in a situation, we're in the bicategory of span. So if you've ever heard of that, then that's what's going on. And the objects are the identity span. So it spans over the set of objects. A span is a set together with a morphism to each of the feet. So what we do to take a composite of an identity with a morphism is that we take a pullback of the objects with the morphisms, but that doesn't do anything, because when you take a pullback along an identity, nothing happens. So if you don't want to think about that quite so detailedly, what we can do is go, well, what we're trying to do is we're trying to get a composable pair such that the first morphism was the identity. So this is going to look like an identity from A to A, followed by a morphism from A to B. So in order to extract that identity, we need to go from C0 to C1 on that component. So we're going to take the pullback of C0 over C0 with C1, because what that means is we're going to take an object and a morphism such that the object is the source of that morphism. So it's not really doing anything, but this enables us to use the identity, the function that picks out the identity, and then we do nothing to F. So inside here, we get our morphism F from A to B together with an object A that is the source of F. So then here, this picks out the identity on A and leaves this morphism the same. And then we do composition. That gets us back down to just a morphism. And that should be the same as the morphism we started with. So in that case, what we can say here is that that actually is isomorphic to C1, and that this should commute. So that gives us identities on the left, and the other way around will give us identities on the right. So that's how that works. Question 13, regarding the note on defining a function on a quotient, could this be thought of as a universal property of quotient sets? Yes. Like dividing by the normal subgroup. Yes, and they're both pushouts. And so it's a little bit circular to do this, but that's basically what's going on, yes. And so a quotient can be thought of as a pushout, or another kind of co-limit, which is a co-equalizer. And finally, question 14, I'm hoping you can speak more about the equalities in the first two bullet points on page 286. Right. I think I understand where the right-hand side comes from, but I'm having trouble understanding how K is being applied directly. So this is in the proof of proposition 19.5 about how to construct pushouts in sets. And a note on defining a function on a quotient, I said at one level, this proof is not going to be completely rigorous, as we haven't really defined quotients completely rigorously. And I think this is what it comes down to, why this proof is difficult to understand, because there's a little bit of sort of abusive notation, tacit assumptions that's coming in. So the idea is that we're looking at this pushout, and we're claiming that it's a disjoint union of A and B, quotiented out by an equivalence relation, which is given by, so this is called S, this is called T, this is called P, and this is called Q. And it's generated by S of C is equivalent to T of C. So S of C is an element of A, so that is in the disjoint union, and T of C is an element of B, so that is in the disjoint union as well. Now, the note on defining a quotient, what I said is that if you define a quotient on V and then you try and map out of it, then the elements of this are basically all the elements of V, except that some of them have been identified with each other under the equivalence relation. And technically what you do is you take the equivalence classes. So you take an equivalence class is a set of elements of V where V and V primed are in the same equivalence class if they're equivalent to each other. And so V as an equivalence class equals the equivalence class of V primed precisely when V is related to V primed. That's not true, because we don't know if this is an equivalence relation. Rats. This is why this is complicated. So I'll just say that if for example, if V is related to V prime, then they're in the same equivalence class. But we may have to generate more things, because, for example, if it's not transitive and A is related to B and B is related to C, that doesn't necessarily mean A is related to C, except we're going to put them in the same equivalence class. So then, to map out of X, you just vaguely pretend that the equivalence relation wasn't there, and you choose a way to map out of V, and then you see whether it respects the equivalence relation. So what you really do in practice to define a map out is you define it on V and then check that if V is related to V primed, then KV is related to KV primed. And that's what we're doing here. So we're going to define K actually on A disjoint union B. So we're going to define K on A disjoint union B and then check that it respects the equivalence relation. And so that's why we start by saying that if A is in A, right, this consists of all the elements of A and also all the elements of B. So for any A in A, we're going to define KA to be F of A, because that's what it has to be. Because P is just going to send A, every element of A, to itself quotiented out, right? The equivalence class of A. So if we're ignoring the equivalence classes, then we just define K to be KA to be F of A, and for all B in B, we define KB to be G of B. And so now we have to show that it respects the relation. So we have to show that if V is, I'm just writing down that same thing again. We have to check this. We have to check that if something is equivalent to, is related to something else, then K sends them to the same place. And so this relation is generated by S of C being equivalent to S, but to being glued to T of C. So the relation is generated by S of C is related to T of C. And so what we have to show is that K sends those things to the same place. So we have to show that K of S of C equals K of T of C. Right? Now K of S of C, and this is where we've abused notation again, because we need to show this for the K that we have produced on the disjoint union rather than the one with the relation quoted out, quotient out. So we have to look at S of C. Well, what does S of C, where does K send S of C? S of C is in A. And so what does K do to all the elements of A? It just does F. So this side is F of S of C. And then similarly, T of C is in B, although really it's that when we quotient it out, it's some kind of equivalence class of things in there. And so then when we do K on the whole thing, we say, okay, well, how did we define K? We said for every element of B, it was going to be G of B. And so it's going to do that. And we know those are equal by the outside. I'm going to pause and see if I can think of another way to express that. Because if you haven't, I can see how if you haven't done things with equivalence, with quotients before, it's a bit strange. Okay, I'll have one last go at doing this with slightly less abusive notation. So what I've decided might help is if we think about this in general, if we think about a quotient as being something where the elements of this are subsets of V where things are related. And I'm going to write that as the equivalence class of V. So it is possible for the equivalence class of V to be equal to the equivalence class of V primed. And so what we're going to say is we're going to define this K this time on equivalence classes. So for all A in A, K of the equivalence class of A is going to be f of A. And for all B in B, K of the equivalence class of B is going to equal G of B. And so now we can go, okay, great, fine. What if that isn't well defined? Where what I mean is, what if there was some element of, if there's some equivalence class such that the equivalence class of A can also be expressed as an equivalence class of B, right? So we have to examine that possibility in case we'd have defined it in different ways. Because what if we said something like, we're going to define a function on the integers mod 4, and I'm going to say that 0 goes to blue, but 4 goes to red. That's not well defined, right? Because 0 and 4 are equivalent in the integers mod 4. So we have to check that whatever we define respects the equivalence relation we're talking about. And so our equivalence relation is generated by S of C is equivalent to T of C. So let's see what's K on the equivalence class of S of C. Well, by the above definition, because S of C is an element of A, we do F on the element of A. And similarly, on T of C, hopefully I did that the right way around. Right, on T of C, on the equivalence class of T of C is actually an element of B. And by what we defined, if we're taking the equivalence class of an element of B, then we get G of that element. But then we use the fact that the outside of this diagram commutes to show it was okay that those things look like they go to different places, because by the commutativity of the outside of the diagram, these two elements are actually the same as each other. And so we're okay. It did respect the equivalence relation. Yes, that was definitely difficult if you haven't done mapped out of quotients before. And then if you work with quotients for a while, you kind of see why you do it like that rather than being more precise about the equivalence relations, because you really do think about the objects rather than the equivalence classes often. So when you're doing the integers mod 4, there are some people who will studiously think of the number 0 in that case as the set containing 0, 4, 8, 12, 16, and so on. I personally don't think that's realistic as a way of doing mathematics. I think that when you think about the integers mod 4, you vaguely think, oh, well, 0 and 4 count as the same, so I'll just pick a representative 4 and make sure that I'm respecting what I'm doing. I think that is all the questions. So I will finish with the praise and appreciation. Did I just say appreciation? I never say appreciation. I say appreciation. I must be tired. Stop share. Oh, I'm so big. Thank you so much for answering our questions. Thank you so much for asking questions. Thanks for being patient with us. Oh, well, thanks for waiting for my answers to come. Great book. Thank you for taking questions. Thank you for answering so many questions on opposite categories. Hearing all those different questions and explanations really helped me finally grasp that concept. I'm very, very glad. Thank you for taking the time to do that. I really enjoy many of your analogies to social justice and your courage to speak openly about them. Thank you, because some people hate them and they tend to yell more loudly about it. And so it's nice to hear appreciation as well, or even appreciation. Thank you. Well, thank you, everyone. Thank you to the Topos Institute for continuing to support us. I look forward to seeing your questions on the next chapter and seeing you next time. Bye.